Okay, so good morning. Iliad said he wouldn't be here, so we're recording so that he can watch it later. I also see Maor and Eitan are not here yet. Maybe they'll join a little later. But it is good to see you, even if only remotely. This is probably going to be the new normal for a while. As you might have heard, the lockdown is intensifying to include kindergartens, which means my baby will be back home, which means I'm going to be less on campus because I'll have to be with him. I'll still try to make the Thursday Astro seminars, so at least when we host people, they can have full attention with no babies crying in the background. But Mondays and Wednesdays are probably going to be just Zoom, either from university if I can get away, or from home. And we'll see how that works. No one is yet registered for Journal Club next week on Monday. So if anyone wants to, you're free to volunteer. I remind you that there are 2 Astro seminars tomorrow. There's our Astro seminar at 5 o'clock as usual, with Greg Ashton from Monash University in Australia and from London. He's going to talk about, like I said in the email, a pulsar glitch, the Vela pulsar and its glitches. So pulsars, as you know, are very, very accurate periodic sources, except that every so often they have a glitch in the periodicity, which we don't exactly know why, how, or how often, or what causes it, related to things like starquakes, similar to earthquakes, or to realignments of the angular momentum of the quadrupole moment. And we can see them. We can see them in the electromagnetic periodicity that shifts, and we can hopefully try to catch them with gravitational waves. So it's a new, interesting type of source, which has not yet been observed in gravitational waves. It was only observed in electromagnetic signals, and it's an interesting object to look for, signal to look for, which obviously has an electromagnetic counterpart. That's the talk tomorrow at 5. Tomorrow at 1, if I remember correctly, is the Hebrew University seminar, which is about the upcoming planned space detectors for gravitational waves. So LISA, Tianjin, Detsigo, and a whole host of satellites planned to launch for detection of gravitational waves. So those are the 2 talks we have tomorrow, both highly recommended. There's still an uncertainty about the talk next week, which was supposed to be Thursday at 5, but there's now a faculty meeting that was just announced this morning for the same time next week. So we might either move it to the Wednesday morning slot or postpone it by a week or 2. I'll give an update when I know what actually happens there. Other than that, most of what I've been doing over the last few days is kind of preparing myself for the lockdown. So making sure I have all the materials for the end of the semester for the course that I'm teaching, starting to look at the material for next semester, and making sure that I don't leave any loose ends when I actually can't make it to campus anymore. How have you guys been? Anyone?
Good so far.
Do you want to expand? How you've been doing, what you've been doing, what you're thinking of doing?
Well, this is the end of the semester, so there's a lot of tasks to complete, and the pressure is rising. And I hope everything will be okay at the exams. And yeah, there's a lot of stress, unfortunately.
Well, stress is part of
Good
life.
luck. Good luck.
Yeah. Obviously, good luck with all
Don't
of
look
it.
very stressed.
What?
I said he doesn't look very stressed.
This is my stressed face.
Uh-huh. What's your not stressed face?
also that face. So it's a stressly symmetric.
Uh-huh. So is there some sort of a saddle point or extremum point in between? Or is it just a flat curve?
Flat curve, I expect, yeah.
Okay, I'll remember that when it's time for the group poker session.
I cannot think for the person from Israel. No, generally Swedish people are like this, constant.
Okay, who else wants to say what they've been up to?
I have done some work regarding my research. By the way, Ofik, you are on campus, right?
Yes.
Okay. Will you have a few minutes to meet with me?
Sure.
Okay. In any case, I'm trying to find the correct expressions at the beginning of the process of the merger and the end of the merger to combine them with my approximates that I predict. So this is my current work. If I will be successful, I might show you some stuff, as Ofik mentioned a few times ago. So just doing my research, nothing more than that, teaching. Hopefully I will have good enough results in order to see the end of this process.
So if you're looking at the approximate for the gravitational wave system, does that mean you're done with all of the tutorials and introduction and the psychiatric problem and all those things?
Yeah, on the surface level at least. I mean, I understand the concept. I understand how to do it. I did it myself, numerically or analytically. But those are, I have to admit that those problems are really simple because they're not involving any. They're not simple in the sense of I could done it by myself without any help. Yeah, but when we are comparing to gravitational waves signals, and especially the fact that there are no analytic solutions in anywhere in that process, in the whole process. So it will be tricky to find an approximate that will be combined well with the signal, especially in the middle part, in the merger part, I mean.
Mm-hmm.
But I'm optimistic, and I'm sure that it can be done. Don't know in what level or in what what will be the quality of the proposed approximates, but it will be okay.
Okay, so two things about that. The first is if the tutorial and example problems are in fact much easier than the gravitational wave problem, you can consider just showing the group what you did with the tutorials or the example problems, even before you have gravitational wave results. So people kind of know, hear a little about the technique and what can be done with it, and kind of practice some of the math skills which are relevant for other people as well. And then when you actually have gravitational wave results, you can present those separately when the time matures. The second thing is that we do have kind of analytical results for gravitational waves, right? We know something about the ring downs. We at least know that it's flat lines. So that's an analytic result. A constant is analytic. It's not maybe not the most accurate because it's only 0th order, but it is analytic. And we know the PN in the early side, which is also analytic. And if you don't find the full PN, or if you want to simplify before going into the full PN, you can even start with 0 PN, right? Just the Newtonian Newtonian approximation, which is also an approximation. It's analytic, and it's always a good place to start, right? We expect the chirp mass, for example, to be determined even from there. So there are always there are always places one can start, even if you have no idea where to go afterwards.
So you say that I can use in a simple example the Keplerian motion in the beginning.
Yeah, just start, see what it looks like, and then you can add
Okay.
more terms, see if it helps, see if it doesn't help. But start off with something, always start with the simplest problem that you can think of. It's not completely, just a zero, but
Yeah.
start with something.
Okay. And do we have some analog to this simple situation in the end of the process? Like instead of quasi-normal modes, do I have some expression that I know that he is like from the zeroth order, but still not well, but still can describe the process at the end?
Leading order 220 quasi-normal mode is basically the zeroth order, right? It assumes that you have a curved black hole with a single mode of perturbation, no tones, just equatorial, the simplest case that you have, just one mode.
Okay. Okay, fine. So we'll meet later and talk details.
Sure. Good. Who's next?
I can go. Hey, everyone. So, as Yehu said, exams are coming up, and there's two big tasks in our courses, which is not great because I dedicate my time during the day sitting and doing the homework, and by the darkness, which is around 5, I find myself with a headache from it, which makes it hard to sit afterwards and read papers or dedicate time to our group work. So that kind of bums me out, but other than that, so okay.
Is this something that happened in your undergrad as well, or when you were on campus, or is it just because of working from home and being cooked up in a room for all day is kind of hard?
I don't know. I think it's just no. It doesn't have to do with the environment. Just the lengthy tasks, the lengthy specific tasks that we got right now. So that's the current situation. It's not something that's going on.
Okay. Obviously, you're master students and you have courses and you have exams and you have homeworks, which is good because homeworks are the place where you actually get to work through your knowledge. You should focus on those as much as you need. Grades are important and doing the work is important. You should, try to keep your head above water. Just, keep some idea of what's going on outside of the coursework. Have what's called keep your eye on the ball in getting ideas, or even just coming to seminars and these group meetings. But obviously, focus on your work and stay healthy. If don't work to the point of losing sleep, headaches, losing weight, all those problems that happen to people when they're stressed. Not to Yehu, but other people when they get stressed. These things can happen. So watch over yourselves as well.
Yeah, thank you. I'll be fine.
Okay. Who else?
What did I miss?
You missed me and Max and Yehu.
Okay. I've been actually having a rough week and a half, I would say. My partner started doing a surgery rotation, so I'm like became a housemate. I did try some things with this thing we discussed about the hydrogen atom, and I read a bit of Maggiore, but I don't know. I can share what I've done with the hydrogen atom, but I don't think I reached any anything, any kind of breakthrough or something. Did you do? I read this paper about Laplace Rungelenz, like the first part. Did it help by any?
Right now, I have all these ideas bumping in my head about the Laplace Rungelenz symmetry and the energy transitions, and trying to kind of put them together, but nothing solid yet. I'm still, still trying to understand whether the spectrum, the correct spectrum, is coincidence or if there's something deeper in it, and I still don't have an answer for that.
Maybe we can tell the rest of the group what was the discussion, or
Sure. You want to?
yeah, just I open my leaks draft. Just a second, and I made like a Mathematica notebook, which doesn't really help. I want to verify that if I get to some results that they exist numerically.
You have a Mathematica license?
No, I have QBTorrent.
You have what?
QBTorrent, but I should not encourage the use of it. Anyway, share screen.
Wait,
Oh, maybe we can do it after the rotation. After we.
Sure. If anyone wants to, I just allowed screen sharing for anyone, but we can get back to you when we finish the round. Okay. Who's next? Should we go alphabetically?
I think I will go now.
Okay.
Actually, except the courses, I haven't much time for anything else. So what I was doing is just trying to complete my tasks and my own works.
Are they going okay?
What?
Are they going okay?
I cannot hear you well. Just a minute.
Are your courses, your homeworks, are they going okay?
Yeah. It's fine, I think.
You have 3, right? You have the 2 master courses plus particle physics.
4. Just atomic physics.
Atomic physics. Okay, so that's a busy semester.
Yeah, very busy. Yeah, that's all.
Okay. Good luck.
Thanks.
Next.
Hey, I can.
Yes.
Last week, I still run some code on the computer, and I found actually the result is good, but they cannot converge and stop. So I try to find the reason, and it may be due to the some parameter didn't converge. So OPEC recommended me to make some contributions to PyCPC, and I find I need to learn a lot. So I still plan to put the tasks of the echo at first, and by the way, learning something about the software and basic knowledge of Python and something. I think that's all. Because I need to devote myself to the homeworks. There are lots of homeworks.
Okay. If you want to tell the group about, PyCBC, the inference, Python inference, the statistical stuff we've been looking into, even just show people how you generate waveforms. with the price CBC approximates. I know Max just asked me about that yesterday for his
Yes.
work. So if you want to show people in the group, even whatever you've been doing already, even if you think it's not a lot, it could actually be a lot for others. So it's good to every once in a while, show people, not just tell, but even actually show some, even very, very, very preliminary, very, very rudimentary, but run some code, show people how it's done. That could help a lot of people.
Yeah, I will be glad to see a waveform.
Okay. Next.
I can go, but I don't have anything really interesting to tell you. I was busy doing my homework. We got a very huge coding project at Statistical Mechanics about Monte Carlo, and it takes most of my time these days. And I also have my quantum mechanics homework and trying to
I wanted to say, Natalia, keep going, learn better for that. You will use a lot.
Yeah. Coding is hard for me, so I'm really trying to figure it out and get some new skills from this project, not only just doing it. That's all.
You use MATLAB, right? You said.
Yeah.
If there's a group MATLAB license, or all the students have a MATLAB license?
I have a MATLAB license because I did a MATLAB course here in Bar Ilan from a year ago or maybe 2 years ago. But I think that we don't have it. Like mine is just left over. No one told me not to use it, so I keep using it. So,
how long is it good for?
I don't know.
I think that they got the 1-year license, all of them as a student.
I think that it's much more than a year for me. So.
You sure you got the license from the teaching stuff?
No, it's the same for me too. It's the same for me too. Since 3 years ago, I did it
And it still works?
in the first year, and it still works somehow. Yeah.
Mm-hmm.
Okay, so does anyone here not have a MATLAB license? Who's doing these programming homework?
I don't got one.
So how do you do the homework?
I don't have.
Wait, Shoval?
Yes, I don't have one, and I talked to Oren. We don't have in our group license. We don't have.
So you can't do the homework?
I didn't start yet, so.
Postponed problems. Okay, and Mao, for you?
I didn't start it also.
Okay. Do you have, Mao and Shoval, do you have experience with MATLAB? Have you used it before?
Yeah, I have.
Yes.
I do it in the did it in the first degree.
Okay.
All of them can do it on R. It's the same simple level.
First of all, you can all do it on R, which is almost identical and works on, I guess, is open source. But I'll try to get if you need it for homework, I'll get a MATLAB license and I'll let you know. Okay.
Ofek, what about mathematical license? If we are already talking about licenses.
Yesterday you told me you didn't need one. If anyone wants.
Yeah, but if we are like in the party of getting license.
I work on on a per need basis. If people have a need for something, I get it. Tell me what you need, I'll get it. People need
I'm saying that I think that there is no discount if you're buying it in the middle of the year. I don't know why Oren said that you will pay less. Mm-hmm. So I think that the need will come eventually. So if you are going to pay the same price no matter what is the date, so we might better buy it now, and that's all.
Does anyone else need a mathematical license? The question is if I get a group license or a max license. So if anyone else wants a mathematical license, tell me.
What's
What
yes
is
needs no.
mathematical license?
Yehu, what did you say?
What is it? Mathematica?
Wolfram Mathematica.
I will show this. I will show this very soon.
It's a license to Wolfram, basically.
Yes, to the full Wolfram Mathematica program. Aitan will show you what it looks like. If you haven't worked with it before, then wait for the demonstration. It does symbolic manipulation of mathematics. Okay, so I'm just going to write down licenses here for myself to remember for later. Okay. Okay, so we were with Neta, right? Did you have anything else to say or just programming? Okay, programming is very important. The main languages used today are MATLAB or R equivalently, which are used for graphical stuff.
And also Python?
C, which is used for high accuracy things or performance critical tasks, and Python for everything else. It would be good if you all know at least two of those three, preferably Python and something else, because Python is kind of the default, and Python can do all the graphics that MATLAB does, and C can do all the math that MATLAB does much faster. So kind of choose which ones of those you use, but programming is an essential part of basically all science done today in exact sciences. So you can't avoid it. And better start soon and get into the hang of it. So it doesn't cripple you when you're actually critical on time and find yourself kind of wrestling with syntax at 3 a.m. with a deadline. Try not to get there. Okay. So I think we have Shoval and Husne remaining.
Yes, so actually, like Neta said, for now, I only do my homework, so nothing else.
Okay.
So I can, in my work, I am progressing a bit advanced. Maybe I can, if you have time, I can share my screen and show some.
Sure, you're allowed, you can do it.
So I had a sample that's like, I don't know if I show, this is the light curve of the gamma ray burst. And here is there is an instrument which is called CVIFT. It has a different instruments, detectors, let's say telescopes on it. It's a BAT for the prompt emission, and then there are XRT emission, and also the optical and UV. And here you see the light curve, flux versus the time. From these black ones are from BATs, and here different mode for the X-ray data. It is VT and PC, photon counting, and the window timing modes. So looking at this light curve, and I wanted there is a flattening. You can see here the prompt expected to be like a pulses, and then the light curve of the afterglow is like generally smooth. There can be some flares, but here what is my interest is this kind of flattening in the light curve. I am trying to understand why there is flattening, and like if it is like looks like if you make the extrapolation of the flux from afterglow to the prompt, which is what is expected, and what is caused here, that why there is a flattening, why there is a missing flux. So this is the main idea. So I had 25 sources. So I compute their isotropic energy also. and I put them here, and I wanted to see how it changed with the TA, which is the TA at the end of this Plato phase. And I wanted to see if there is any correlation and if there is what it is. Like I see some kind of correlation. Different colors represent some kind of flux ratio that I get from prompt to the plateau here. This plateau, I call this flattening plateau, to the prompt. And if it is larger, which means that this flux is close to this flux, then it is blue color. And if it is smaller, and then they are red. So you can see some kind of like higher value of the isotropic energy is mostly like the plateau and the prompt are like afterglow. They are more close to each other. So, but here there's some interesting trends, and I also check if there is any bias effect here. The work is going on, but what we find something like when I also check the flux ratio of the prompt but to the plateau, I find some kind of like 4 order of magnitude differences. And so the idea was that if you see that this flux ratio is equal for all of them, so you can say that there is some central engine activity. But as you can see, and we don't see this the same like lying in one certain number, and there is differences. So then we say maybe there is density going on. So there is one work called the density jump. So they run some hydrodynamic simulation, and it depends on the Lorentz factor. If the shock has a Lorentz factor like 23, and it encounter the Lorentz factor, the shock is going with the Lorentz factor 5, then this jump can be, I think, can cause some kind of flattening. But then there is the point that when I was searching like bias effect, that like somehow when I put these sources,
Husne,
yeah,
sorry for the interruption,
yes.
but all the data that you show here is from simulation?
No, these are all the data are from the satellites, Swift
Okay.
30 and BAT instrument. So prompt and afterglow, because the gamma ray burst has 2 emission mechanisms, mainly like prompt. Of course, there are like photospheric and different things, but the prompt and the plateau, sorry, afterglow. So this is from.
Like, what is the difference in the colors here between the black, red, blue, and green?
Yeah, so it is first I explained that this is the black ones are from the BAT instrument, which is for the prompt emission. It is it happened, as you can see, in a shorter time.
And that's gamma rays.
Yes, it is the gamma rays that you detect that it is a gamma ray burst. And then after there is afterglow. In the afterglow, the process is evolved with the density, interstellar medium or wind medium coming from the.
Yeah, but what's the color coding here? The blue, red, and green.
So the data points are the different mode, because there is a VT mode and PC mode, and then VT slow mode. So the different mode of the instrument has different data points. But here there is also the blue points that I pointed. This is I am trying like interpret extrapolated light curve. So I am extrapolating the afterglow light curve along this side, and I am trying to understand what it causes here. And so this.
So for example, the green, which is which has the plateau, is that also gamma rays? Is it a different energy of gamma rays?
So this is the between like the flux between 0.3 to 10 keV is obtained from the X-ray XRT instrument in the photon counting mode. It's like window timing mode and photon counting mode. So this is the obtained from that. and it's supposed to be afterglow.
Okay, so then the black, blue, red, and green are all in the same wavelength or the same type of
Yeah, you can
photon?
say that. So this is also, sorry, this black ones is the 15 to the 50 keV energy range, which is BAT instrument. For the X30, it is 0.2 to the 10 keV in the X30 observed. So yeah.
So the black is one type and the colorful is another type.
Yes, exactly. In other instrument, and instrument has a different mode as well.
And okay, the modes. Okay.
Yes.
And I also have a question about the black one.
Yeah.
Why it's so noisy?
So this is another like presentation. You know that it is gamma ray burst has a lot of spiky shape. Like it can be several spike. This can be one smooth spike. Like how to say? It's the light curve shape, and depend on the emission mechanism. You see like smooth light curve or spiky light curve. So this is the like you can measure the width of this. Like in each pulse can present different emission. Like it can be a photospheric emission or like synchrotron emission, or depend on like this is the interpretation that people do. But this is the normal phase that you expect. For example, as you can see here, it has a very high, more spiky. Here you see more smooth. This is a BAT instrument. Energy range is smaller. And if you go to the GBM, Fermi GBM instrument, you will see more different shape as well there. And it's more energetic. So this is normal.
Okay.
So you should notice that all the times here for the prompt part, the high part, I think they look like they're about, what, 10, 20 seconds, something like that?
Yes, exactly.
So that would make them long GRBs.
Yes, they are. I mean, I didn't separate actually the long and short, but since my selection criteria was to have the data on the very late afterglow, so then the short GRB doesn't have like this long emission in the afterglow. So then they just fall in the long GRB classes. Yes.
So another thing, usually you want to see in a GRB, or you often do see in a GRB, is that it's not just spiky, right? The black part, look for example at the left bottom, 08, 0721. You can see that it's not just noise, it's systematic, right? There's like a period, it goes up, it goes down. It's not noise, it's more variability which you can associate with characteristic times of the source.
When you extended it, you will see clear light curve, like going like this. Yeah, I don't have the here like right now to show, but I don't want to take too much time for you, and I just wanted to go to the point. Like then what I did, since there is this this density job, and I wanted to see and if we can run hydrodynamic simulation, but however, there is some like maybe it's not the density because the this plateau doesn't affect it. I mean, the selection is the late afterglow, but it doesn't affect the plateau because.
Why are there gaps?
Sorry.
Why are there gaps?
So these gaps is depend on the like. Depend on the instrument as well, but depend on also maybe the source is not emitting. So because I have these gaps when I start to study also the source with like sorry. So the next step is to select the source without the plateau. So and here our aim is to have I was saying maybe now it will be more clear, spectral index and decay index of these sources. You can see this purple one with the plateau, which has plateau, and the others doesn't have a plateau. So then now we are comparing, these are the regions for the environments, like wind environment or interstellar medium. So then if there is jet brake, it is like you see the jet brake, something like if you see some brake very with this quite steep afterglow and you see the jet brake. So this is some kind of comparison. And as you can see, they are more concentrating on this region. However, our sample with the plateau is in this region, but the separation is not so clear. So this is the next step that I am doing. So I was also finding that if there is a jet brake here, and what is the earlier slope? So then, as you can see, they are all concentrating on that region. However, ours is mostly, we are thinking that it is in the like green region, the one without plateau, and one with the plateau, it's mostly on that region. I mean, we also check other jet brake. So things are going on. Then I come to that point that I see more a gap in the sources without the plateau. So this will be another question that like, okay, I cannot decide here, there is no plateau. Sometimes I am saying that, okay, I assume that there might be here the plateau because there is some flattening, but it's not clear because I'm missing the data here. And normally because I select my sample at 250 seconds, but there is no data. So how can I say that there is no plateau? So depend on the different source. If you want to go by source, it's difficult to interpret. But with the sample, maybe we will have some clear. So I mean, I think in the following weeks, main idea is to discuss the physics. Like we are discussing, but still to go, if you want to run the hydrodynamic simulation that from the paper of Van Etten for the density jump, or to check also there is another idea to include the optical data. If you find the optical data in this gap, from the Swift satellite, there is no, I check it. But maybe from the telescope, ground-based telescope, there might be data, and we need to check if there is flattening or it is more steep. So yeah, this is the question to ask in our work as well. Yeah. But sometimes it can be the link with instrument, but it cannot be for all sources. So yeah, we need to see. This is going on. It's quite.
Do you have like, I guess, technical readouts from the instrument about those times, telling you if it had any issues, malfunctions, if it was behind, hidden someplace, pointed in a different direction, anything like that?
Yeah, you can say that, for example, between the BAT and VT mode, for sure it is possible. And because it is a different instrument. So it's normal that you can have a lack of the data. Mm-hmm. And then you come to the question here, the VT and the PC mode, there is also a gap. It's more, sometimes you can say instrumental effect, that the instrument missing the data. And then if you want to interpret, then you cannot interpret because it's a lack of the data. And another point is why always in that time? Yeah. There are guidelines. Maybe I should keep going. I study for my PhD this instrument, so I know. I studied the late afterglow for low luminous gamma ray bursts. I know most of the things, so how it is, instrumental effect and so on. But maybe I need to go and update as you ask. It's a good idea. But our idea is to find some optical data to fill this gap if it is possible. But it's possible that we will not have because it is a shorter time. Yeah.
It just looks like most of these gaps are actually like you did extrapolate, and it looks like a straight line with just a hole. So it doesn't. I don't know if there's a mechanism in the source, or if it's the instrument, or if it's something in between that came and obscured the gamma rays.
Yeah. Yeah, so the first idea that indeed to eliminate the instrumental effect. The second idea is to eliminate the selection effect based on the source. And then the question will come, what it causes, why it's always in this region, and why you have the data when it is plateau, but where you don't have mostly the data when it is not a plateau. So, I mean, the instrument capable to observe this for the other sources, but not like.
So if I look at 08, 04, 11, it actually looks like it should have been a plateau, because if I continue the line, it will not reach the top.
Yeah, yeah. So if you follow this blue, you see, it is looks like this. There is 1 point here and 1 point here and 1 point. It just looks like flat. Normal line. How to say?
Straight.
Straight line. Yeah. So, however, it's possible. Yeah, but there is no VT data, for example, for that I can say. So for this source, I assume that there might be plateau, as you say. But for example, here, I didn't assume that there is plateau, for example, because of the, also the assumption is depend on the, how flat this, because it can be like 0. I just discarded below the like 0.7, the K-index. But some people, for example, Dianeti, that I am sort of working on her sample, she also include like slope 0.55, 1.2. So yeah, this is
okay.
These are the questions that I am trying to solve and ask clear, of course, come to the physical interpretation. Yeah, and so maybe I can stop the sharing. This is
cool. Thank you. Actual experimental observational curves.
Yeah.
With all the mess that comes with it.
Yeah. It is for me now. I know what to do, and there is no like dealing with all small details, like how to understand the instrument, how to the code, and how to write the code. These are like, and then you just make the science. But it's important to understand the first basic, and then you can build easily. Yeah.
Cool. Thanks. Okay. Anyone else? I think we are done with the round, right? So now it's open stage. Eitan, do you want to start?
Yeah, I will start. First, I forgot to mention it's my birthday today.
Mazal tov.
Mazal tov.
Happy birthday.
Mazal tov. How old are you?
Guess.
32.
6.
Oh, wow. You're my age.
Yeah, I'm half a year younger than you. Anyway, the question that was raised by Ofek, we read this paper about quasi-normal modes under some approximation, and we get a result, like the approximation uses the fact that we use very high L, like in the, how to call it, the representation, not the representation, like the spherical, how do you call these functions? The not spherical harmonics, like
spheroidal harmonics?
Spheroidal harmonics, yeah. So use like L goes to infinity, and the results you get through this approximation are still valid to L equals 3, which L equals 2 is the minimum. So Ofek suggested that in hydrogen atom, like Bohr's model is a model that comes from wrong assumptions, but gives the exact correct results. So maybe there is a way to see how you, what is it coincidence, or is it like, is there some kind of hidden mechanism that creates it? Like the correspondence between Bohr's model energy spectrum to Schrödinger equation exact solution. So I haven't done much about it. I tried a few directions. I'll share my screen. Okay, screen. Forget about this. So if you use the virial theorem, first I reviewed, for anyone who doesn't remember, for the first course in quantum mechanics. Bohr's assumption was based on the de Broglie wavelength that the angular momentum of the electrons move in circular orbit around the core of the atom, around the nucleus, and the angular momentum is quantized by integer units of h bar. So if you use if you compare like the centripetal force to the Coulomb attraction, you get a relation between the speed, the velocity, and the momentum, the angular velocity, and comparing it to like putting it inside the equation of for the angular momentum, you get quantization over the radius, and similarly you can get quantization over the energies that goes like 1 over n squared, which, as we know, is the same relation we get from the Schrödinger equation. What I tried to do here, but I didn't get to very good results, is to use the virial theorem on quantum mechanics, which states that if you have like radial potential, then the expectation value of the kinetic energy equals to 1/2 the expectation value of the potential energy, and of course therefore the energy equals to 1/2 the potential energy or minus the expectation value of the kinetic energy. And if we compare these two terms, we can get to the following equation, that mu, like the reduced mass of the electron mass, basically, times the expectation value of 1 over r equals to the expectation value of the radial momentum plus the expectation value of angular momentum square over r squared. What I was basically trying to achieve is to define this to, I tried to find the commutation relation between PR and like radial momentum and 1 over r, and then like use the uncertainty principle to find like a minimal energy for a given radial momentum. Ideally, I would like to get to a point where you have an equation such as this, where instead of n, you have the solution from the Schrödinger equation, which is, instead of n, you have k plus L, where k is a natural number. But k is depends on quantum quantities, like some kind of uncertainty or some kind of expectation values, which if you take it classically, they commute. If it's not classical, they don't commute, and then you can see how in the limit, in the classical limit, you get the correspondence principle, like it stays the same. That's what I tried. I didn't reach any kind of conclusion of anything else. There is also the Laplace-Runge lens, which Ofek mentioned. I don't have it open in my browser now, which is a way to get this, using the full theory of quantum mechanics, to get the correct values for the energies. but this doesn't use like any differential equation. It skips the Schrodinger derivation. You don't get the wave functions, but you get the eigenvalues of the Hamiltonian very easily this way. What I did notice that in this equation, if you assume that if you assume the following, which is basically the classical thing, that 1 over r squared equals to 1 over r to the expectation value of 1 over r squared, like you don't have any kind of variance, and you assume that, just a minute, that PR squared equals 0, then you get like, it's the exact same derivation as the quasi-quantum derivation, the semi-classical like Bohr's derivation. If you assume that this one equals 0 and L squared, but this is not surprising at all. It just means that
PR equals 0 means that there's no radial momentum, so it's a perfectly circular orbit.
yeah, and that L square equals to H bar square L square, which means you don't have any kind of uncertainty, like the commutation relation between the different angular momentum operators, Lx, Ly, and Lz equals 0, which, as we know, it's not true in the full quantum mechanics.
Mhm.
Okay, that's all I have to say about it. I've been also reading like Major. I think I'm about to finish the theory in a couple of weeks, the theory part of the book. So
That's part 1.
there is like 2 or 3 more episodes in part 1 about experimental, like about interferometers and data analysis and something extra. I don't remember.
Wait, so data analysis, that's in volume 2, right?
No, data analysis is
That's in 1?
volume 2 is different phenomena, how their gravitational waves should look like. It starts with supernova, then pulsars, quasi-normal modes, and in spiral and cosmology, if I recall well. Anyway, I thought about maybe instead of one journal club to make some kind of lecture of the first few episodes to get to binary, to the spiral of binary, like the wave pattern that you should have from it, like all the theory that builds up to it.
Sure. If you want to do it for next week, Monday or Wednesday, just say so. If not, we can also do it later.
I need to prepare it, but yeah, Wednesday may be possible. Monday is, I can't guarantee. This weekend is busy.
Do you have any plan for celebrating the birthday?
In lockdown, I'm just gonna cook something.
Lockdown only starts tomorrow at midnight.
Today, I'm not gonna celebrate anything. Tomorrow. Okay, that's what there is. Yeah, there is also this part, but I didn't. That's another way to try to define the energies with the uncertainties in the part of the equation. Nothing. I didn't get any results. Yofik, do you have anything to?
Nothing concrete, sadly.
Okay, I stopped my screen sharing, so.
Wait, before that, does anyone have any questions or comments? Do you guys understand, guys and girls, understand what Ethan and I are trying to do here? Why what the problem is, or what the context is?
If you want to explain it with your own words, it would be good.
Okay, I'll try to share my screen. Let's see. Haha. So we have the Bohr model for the hydrogen atom, which is particle travels in a circle at some radius r. There's a center which is positive, the electron is negative. Let's assume that the electron mass is mu and that it's completely negligible relevant to the nucleus energy mass, at least 2,000 times greater. So we have the momentum. If it's a perfect circle, then there's no radial velocity, there's only tangential velocity, which is v. So we have momentum mu v times the radius r. These are all constants, gives us the angular momentum for the hydrogen atom Bohr electron. And he assumes that this is quantized by a quantum number, which he calls n, but maybe we can let's use a big n times h bar. Or maybe without the bar, I don't remember. All right, this is the Bohr quantization condition. Everyone remembers this? Okay, what also happens in this classical derivation, the centrifugal force, mu v squared over r, is equal to the electric force, which is z, which I'm going to assume is 1 for hydrogen, e squared over r squared. I also assumed k equals 1, just trying to ignore as many things as I can. Which means you can combine these two. You can get that v equals nh bar over mu r. Substitute that in the force equation, you get mu times nh bar over mu r squared divided by r. This equals e squared over r squared. So now we get mu n squared h bar squared r cubed mu squared. One of the mu's cancels out. Let's move r to the left and e to the right. So we get r equals n squared h bar squared over e squared mu. Is that correct? Did I miss anything? Eitan, are these the correct radii?
Just a second.
Basically, this is
You got the
Coulomb.
same result with Z they bottom because they assume like.
Yeah, I ignore Z. So this is just Coulomb's law for electrostatics, for circular motion, and this is angular momentum. So this was all completely classical, and of course we get this n quantization. So this is Rn, and you can get the energy levels from this, En, and the energy is minus E squared over R, right? That's electrostatic energy. It's the integral of the force. So we get minus E squared divided by n squared h squared, and up we have E squared mu. So we get minus e to the fourth mu divided by h bar squared, 1 over n squared. So there's a prefactor, which will get the units of energy correct with all the transfer. And you can put the k and the z and whatever you want in there. But then we get here the hydrogen spectrum. So this, if I remember correctly, this number is 13.6 electron volts. And so you get that the energy levels are, minus 13.6. And then that's for n equals 1. And for n equals 2, you get a quarter of that, so minus 3.4. And then more and more energy levels kind of approaching at n equals infinity, you get the energy 0, which is the free ionization or a free electron.
Ofer?
Yehu, you were asking something?
Yeah, about the energy term,
Yes.
you didn't take into account the kinetic energy?
Sure. So there might be a half in there because this is the potential energy, and like Eitan said before, the virial theorem for this potential means that the kinetic term is minus half the potential, so we get another factor of 1/2. So let's put another
Okay.
2 at the bottom everywhere. Okay, so we get these energy levels. They're quantized by a number n, and the meaning of n is actually quantizing the z component angular momentum. Right? In the quantum language, this is not the full angular momentum of the system. This is just the z component of the quantum system, because you can never know exactly the full direction of angular momentum in a quantum system. And this should be equal to mh bar, where m is the z component angular momentum quantum number. We further remember that if we actually write down the Schrödinger equation for the hydrogen atom, you get that the energy depends on well, there are 3 quantum numbers, n, l, and m. L and m are the spherical harmonic numbers. They come from the Laplacian and spherical coordinates. N is a number that had no meaning in the classical context. It kind of enumerates how far the particle is, or some sort of it basically determines the energy in the sense that in quantum mechanics, I mean in Schrödinger quantum mechanics, so the full, not the semi-classical Bohr model, but the full Schrödinger model, you get En equals the same, let's call this number R for the Rydberg constant, or let's just call it EH0. You get the same EH0 times 1 over n squared as the eigenvalues of the Schrödinger equation for the hydrogen potential, which is Hamiltonian equals p squared over 2 mu plus, or rather minus e squared over r. But now this h is an operator, this p is an operator, and you can think of this r as an operator, even though it's just in the space representation, it's a coordinate, but otherwise it's an operator. And this, of course, gives you a differential equation which you have to solve. It has eigenvalues and eigenfunctions, and the eigenvalues are these. So the energies are the same. You can say that you get the same En, big N in the classical model equal En, small n, in the quantum model. But these n's mean something completely different. For example, for n equals 1 in the quantum Schrödinger model, for n equals 1 in the Bohr atom, the wave function, or the position of the electron, is spherical. It's exactly at the radius a0, which is the classical hydrogen atom radius, 0.5 angstrom, and it goes around in a circle. There's no spread outside or inside of this radius. It's a fixed radius.
I wouldn't say it goes around in a circle, because L equals 0. It doesn't have any angular momentum.
Right. So this is n equals 1.
Point energy.
Exactly. This one in the left is capital N equals 1. That's a classical system. The quantum n equal 1 system looks like this. Right? It's smeared lighter and lighter. It's kind of maybe centered around this this A0, it's also as kind of a typical radius, but L here is 0. L is 0 and M is 0. There is no angular momentum in any direction, and the radius is entirely smeared.
The mass probable radius in this case is actually 1.5 A0, not A0. And not the mass probable, the expectation value. The mass probable is A0. The mass probable.
Yeah, it's even, let's clear the center a bit. It even gets kind of lighter again towards the center. So you get kind of this something that is maybe related to the classical trajectory, because A0 is kind of this similar, maybe up to a factor of a few, of like 1 and something. But it's not spinning, there's no angular momentum, and it's not localized, it's everywhere. So these kind of pictures look very different, but they give the exact same energy. And it works at any n, right? It works for n equals 2, n equals 3, and n equals 4, and going up and up. And the quantum systems in this case, well, the classical systems are just wider. You just get that it's spinning further out, and so it has more angular momentum and more energy and closer energy to 0, etc. The radius grows. But for the quantum higher terms, higher modes, you get crazy things, right? You get that you start getting zeros and rings with dense, like getting light in between, and then dense closer to them, and you get peaks and you get troughs and you get all sorts of these weird things happening in your modes. And the question is, are these two things related? They have the exact same energies, and that's strange. And this is all like 1930s physics. But then we get something that, to me, reminds of that in gravitational waves. Because on one hand, we said that if you look at a binary system, say a big black hole, on the one hand, you can think of a big black hole, and then you know that you have the photon ring. If it's a Schwarzschild black hole, it's at R equals 3m. And you can do classically draw the effective potential. And it looks something like this. Classical potential for photons, which means G mu nu, U mu U nu equals 0. So the velocity is normal, the forward velocity is normalized to 0. And then you get an effective potential term. And so you say that an unstable circular orbit will appear here. And this is your R light ring. And this is equivalent to the circular orbit in the Bohr model, the classical planetary model of an atom. And if you take this radius and you derive the frequency from this, the frequency of orbit at the light ring, or the frequency of gravitational waves coming from the light ring, so twice the orbital period because it's a quadrupole moment, you can kind of build a quadrupole source that's traveling at this radius at the proper frequency for that radius from the modified Kepler's law or something like that. And you get a frequency of the light ring. Okay, and you can actually see that the frequency of the light ring is not only given for a Schwarzschild black hole, it's given for a Kerr black hole if you include spin A. And you get some curve with spin and light ring frequency, or light ring gravitational wave frequency, and you get some curve that looks like that. It terminates at 1. And this is Schwarzschild, A equals 0. And this is a completely classical derivation, a classical relativistic derivation. There's no quantum, there's no discretization of waves or of modes. You write a potential for a particle, which is a photon moving around in a circle, and you find this curve for the frequency. You can actually even look at this peak and kind of expand the next derivative, and that will give you the damping time, because how steep the potential is will tell you how fast these light rays are diverging away. So you can think of the position as giving you the frequency, and the curvature giving you tau, the damping time at the light ring for gravitational waves.
Okay.
And that's another curve that you can draw out.
Ofek,
Yes.
why you say the fall velocity is 0?
The fall velocity is not 0. The fall velocity is normalized. The length of it is 0, right? If you remember special relativity, in special relativity, for velocity, for example, for a photon traveling in the x direction, is 1, 1, 0, 0, right? This is the time component, and this is the x component. So dx dt here is 1, or c if you want to reintroduce the speed of light. And so if you normalize it, you calculate eta mu nu u mu u nu, you get 1, 1, 0, 0 minus 1, 1, 1, 1, which is the flat Minkowski metric. Let's move this to the side. One, 1, 0, 0, and then you get minus 1, 1, 0, 0 times 1, 1, 0, 0 minus 1, 1. This is 0. So the 4 vector is not 0, but it is null. It's absolute value, right? This is u squared. This is the absolute value, or the length of the vector. The length, or the norm of the vector, is 0, which means it's a null vector. It's a light-like trajectory. This is opposed to a particle. For a particle, you would have velocity which looks something like gamma, beta gamma, 0, 0. And then if you normalize these, of course, gamma is always greater or equal than 1, beta is always less than 1. Beta is v over c. And if you normalize that, gamma, beta gamma 0, 0, minus 1, 1, 1, 1, gamma plus beta gamma 0, 0. Then you get minus gamma, beta gamma 0, 0, gamma, beta gamma 0, 0. So gamma squared minus plus beta squared gamma squared. And this does not equal 0, right? This is gamma squared, 1 minus beta squared. There might be a plus, which I missed out in some of these multiplications. But basically, from the hyper trigonometric functions, right, you get an identity that this is 1 over gamma squared, or rather that gamma is 1 over 1 minus beta squared square root. So you put these in together, 1 minus the beta squared. So you get that this equals 1 in these units. So a massive particle, which has to travel at below the speed of light, the time component and the space component have to obey this relativistic relation that the velocity normalizes to 1. For a photon, it normalizes to 0. For a particle with mass, it normalizes to 1. Right? This is special relativity, but it carries into general relativity, which is why we have a separation between light-like trajectories and time-like or massive trajectories. This potential is then, for the light ring, is given by the light-like trajectories. So I put in that the norm has to be 0. And the result then is I can have this classical GR derivation where I calculate trajectories of geodesics of photons in my space-time, which is a fixed space-time in this case. I just assume that the background is fixed and put a trajectory there. And I get this curve for the frequency. A completely different derivation for what might be related to this system is the quasi-normal mode derivation. Quasi-normal mode is kind of a quantum derivation because it deals entirely with discretizing waves on some background. Right, in the quasi-normal mode case, I don't say that I have a particle rotating around some black hole. I say that my space-time is a perturbed black hole. In particular, we can look at the perturbation with L equals M equals 2 in terms of spherical modes. L equals 2 means it's a quadrupole. So the leading order perturbation here might look something like this. If this is a circle, a perfect circle, then an L equal 2 perturbation can look something like this. Kind of spread out a bit. Okay? A dipole would be tearing it to one side and having minus on the other side. We don't have minus mass in the universe as far as we know in gravity, so we kind of pull a quadrupole. And if we say that this quadrupole is rotating, as a quadrupole, there's some angular velocity because m equals 2, so this whole perturbation is in the plane of rotation. Then we can say that this perturbation is kind of spinning. But again, what does it mean that it's spinning? We have to think of the perturbation as something complex, and the thing that's really changing is just the phase in some sense. So you can think of this as the real part, and maybe this as being the imaginary part. And then an instant later, it will be reversed. You'll have this as the real part, and this as the imaginary part. So we kind of have this perturbation of our space-time, and this perturbation is not stable, it's decaying with some rate, and there's a frequency of the rotation associated with this perturbation. And so you find F L equals M equals 2 and say N equals 0, which is the overtone. And you have tau of L equals M equals 2, N equals 0. And these come from solving quasi-normal mode. So I'll write quasi-normal on top. And these come from solving linear perturbations of wave equations and looking for eigenvalues and eigenfunctions of those operators. So again, a kind of quantum derivation similar to the Schrödinger equation. In fact, in the end, you solve the Schrödinger equation in this case for the effective potential and the perturbations. And what turns out is that this F, Q, and M, which was derived in a completely different fashion, looks something like this. And the differences between them are something like 5% at most. So it's not an entirely perfect correspondence like you get for the Bohr and the Schrödinger model, but it's very, very, very close. And these two derivations are completely different. They come from different physics, different assumptions, different mathematical procedures, but they give the same result. And so the question is, can we learn from this simple hydrogen atom system, which we all know from undergrad, and kind of see how this correspondence plays out here, and why does it work so well? Now I can add that when L goes to infinity, we understand the correspondence. Because L equals infinity means or that you're basically going to a particle limit in the wave case. You're basically saying that your angular resolution is getting higher and higher as L increases. And you're basically looking at the decomposition of a particle in what's called partial angular waves in the language of quantum mechanics. At the high L limit, it actually does turn into this perturbation that's traveling around at the right frequency. And then you can say it's trapped by the potential and it has some leakage, and the correspondence kind of makes sense at high L. Extending it to this L equals 2, the lowest possible L, and still remaining so good is a question that one needs to answer. How can this be such a good approximation? What's the underlying symmetry or physics or mechanics that's going on? And because it's a difficult problem, I don't know the answer, I was kind of suggesting to Eitan that we look at the quantum hydrogen atom case. Oh, another correspondence or complication I should mention is that the perturbation of gravitational waves in quasi-normal modes is not localized, right? Again, it kind of goes everywhere in space. It's infinite, and it might be more dense close to the black hole, but it goes everywhere. It's spread out in R, very far out, similar to the hydrogen wave functions, which are kind of spread out. They're centered around the right radius, but they go out much further out. And of course, you cannot just say that it all turns together, that the spread out function turns together at the correct velocity, because the underlying physics here is Keplerian. Coulomb's force and Newton's law are the same in the sense of the radius to velocity relation. And that means that the further out you get, your frequency should go down. The closer in you get, your frequency should go up. In no case should this wave function just rotate at a rigid body if it's spread out in R. Yet it seems that it does, both in the quantum sense and in the gravitational quasi-normal mode case. So these are all kind of mysteries, which I think are interesting to look at and to try to understand better. Eitan, anything to comment?
Not so much. Can you go back a little? Like the correspondence I saw in the paper was like in the beginning about this, the orbits closing on themselves, like this degeneracy in the orbits. I don't know where this graph is from, where you're like
this one?
Yeah, I may have missed it or didn't give it the right attention.
It's not in the book and it's not in the paper. But it is something you can very easily do for yourself. I even give it as an exercise in the astrophysics course. You can you take the QNM numbers, frequencies and damping times, from any tabulation of quasi-normal modes for a black hole. So Berti and Cardoso, QNM, they kind of give the standard tabulation in the field. And it comes from solving eigen values of the potential. So we have the Tukhowsky equation. It's a differential second order equation, kind of what's called a Sturm-Liouville problem. You find the eigenvalues. Berti and Cardoso did that, and they give you numbers. So you plot the red curve.
It's not numerical solution, it's analytical?
It's finding numerically the eigenvalues of an analytic equation.
I think it appears in Majora or it's mentioned. Like
I'm sure it does. For the Majora mentions it because he solves it for Schwarzschild. He doesn't solve it for
Yeah. But he shows it.
He explains where the equation comes from for Tucholsky equation in Kerr, but he doesn't actually show or solve it.
Yeah.
But the equation is analytic. Tucholsky derived it in I think the early 80s, late 70s, early 80s. Lever gave a numerical recipe for solving the eigenvalues. Bertin Cardoso elaborated and tabulated these results. So those are known numbers. The result of the eigenvalues of this particular equation, which depends on A. The green is even simpler. The green is fully analytic. The green is plot out the potential depending on A, solve for the radius where you have the potential zeroing out. So the peak of the potential, that's a circular orbit because there's no force in any direction, no effective force in any direction. So you have the radius. Now you know you have a photon geodesic at a particular r with r dot equals 0. So you just plug r equal that and r dot equals 0 in the normal. For example, the equation of normalization for velocity on the Kerr background, or just solve solve the geodesic equation on a Kerr background with that r and no radial velocity. Both of those are trivial integrals to do. You don't need, you can do them by hand. You don't need numerics for that. And then you calculate how long it takes to come back, what the period is, and you get the green curve. So the green curve is completely analytic.
We're talking about Kerr black hole, about equatorial orbits, not like...
Yes. This is L equals M means that it's equatorial. Equatorial, and completely analytic, and they close, and they match.
I had another direction I tried to think of is like actually to do the correspondence principle, to look about very big N and L equals N, which you can basically think about two-body problem in macroscopic scales even. And but using the quantum formalism, like to get the orbit, like let's say I start with N, L equals L, N minus 1, and M equals L, and to measure the distance and the velocity in like very small time intervals, given a certain uncertainty in both, and to see like how I get the orbit, but they didn't, maybe to use the dispersion relation with the Hamiltonian as the evolution in time as the unitary operator, but they didn't, I don't think I can get any insight. I'm not sure I can get any insight because the average momentum, like the expectation value will be what we expect classically. So I don't think.
I'll have to, we'll have to sit and look at that more deeply, see what happens there. Does anyone else follow the problem, the different modes, the explanations, the two different regimes, and why it's surprising that they match? I should maybe mention another thing, and that is that unlike the classical hydrogen atom case, where h bar came out as the quantification constant, here there is no quantification constant, right? H bar doesn't appear in any of these derivations. The quantization condition here is not that the angular momentum be some multiple of h bar. It's that if, as I can mention from the paper, that the orbits maybe close on themselves, the functions are consistent, so they close around in some multiple of the radius of the system. But that means that the inherent constant determining the quantization is the mass of the system, and it scales with the mass of the system. So these are classical, discrete wave, non-quantum modes. It's kind of an intermediate problem between classical mechanics and quantum mechanics. We have wave discretization, but there's no H bar, there's no quantum gravity involved. And another interesting step might be to see how that develops into quantum gravity in the relevant regime. How do these quasi-normal mode waves translate into quantum perturbations of a black hole when everything that's left is just quantum?
Ofer,
Yes.
what was the explanation in the Schrödinger equation and the Bohr model that the energies came out the same?
I don't know the answer. There are a lot of people writing about kind of relations or why the math is similar. The Laplace-Runge length is one of the kind of something that gives a symmetry between angular momentum and the radial potential part. And that might be related or have a part in the explanation, but I don't have a full explanation that I understand kind of in its simplest form to see why that had to be this way and then to build on it. It's kind of a fundamental question in quantum mechanics, which I did not yet find a satisfying solution for. If any of you have one, you're more than welcome to suggest it. Any further questions?
I have something
Yes.
if no one have anything else. I've been reading a little bit about the Gertenstein effect.
How do you spell that?
Gertenstein effect. Yeah, GR. Just let me check.
I expect T.
Send it in the chat.
Gertenstein. Interesting.
It basically
Either-
says that if electromagnetic radiation goes through a magnetic field, it may produce gravitational waves. It's from the 70s.
Why?
It was pretty harsh paper, but they said something about that the magnetic field turns spin 1 into spin 2, something got to do with the particles, and they mentioned gravitons. So I'm not sure how well defined everything is.
Is this high energy? Is this in matter?
This is a matter thing, I think. I can send it to you later.
Yeah, I haven't heard of this effect. So everything I'll say will be guessing. But if you send me the paper, I can kind of check it out.
Okay.
Anyone else?
I'm sending something in the chat that may relate to the problem we mentioned. I'm just starting to review it. It's not a paper, it's a website that describes a Sommerfeld model, which is elliptical orbits for electrons. Like it's kind of intermediate between a Bohr's model to the Schrödinger solution, I guess.
Okay. Anything else? Anyone? Questions, ideas, problems, complaints? I think we might have lost a few people. Anything? Okay. Then good luck with all of your homeworks, and I'll see you tomorrow for the seminar, 5 o'clock.
Thank you.
Bye.
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 Bye.